Holiday and Resnick, Chapter 5, Problem 28. A car that weighs 1.30 times 10 to the fourth newtons is initially moving at 40 kilometers per hour. When the brakes are applied and the car is brought to a stop in 15 meters, assume the force that stops the car is constant. Find A, the magnitude of that force, and B, the time required for the change in speed. If the initial speed is double and the car experiences the same force during the braking, by what factors are C, the stopping distance, and D, the stopping time, multiplied? There should be a lesson here about the dangers of driving at high speed. Well, I see we're going to use a kinematic formula to find the acceleration first. So I'm going to use this formula. V squared final is equal V initial square minus 2 times the acceleration times the change in position. We know V's final is going to be 0. So we're going to have V initial squared is going to equal minus 2A delta X. And so the acceleration is going to be V initial squared over 2 times the change in X. And that's going to be, I'm going to do some computation and I'll get right back with you. So when we solve for the acceleration, we get the acceleration being 4.11 meters per second square. Now we have the weight of the car is 1.30 times 10 to the fourth newtons. We want to divide that by 9.8. to get it into kilograms. And when we do that, we'll get the car weighs 1,326.53 grams. And we want the force. So for A, F equals MA, which equals 1,326.53 kilograms, and this should be kilograms. When you divide gravity into newtons, you get kilograms, times the acceleration, which is 4.11 meters per second square. And when you do that, you get 452 times 10 to the third newtons. So that's your answer to part A. 5.452 times 10 to the third newton. We use the kinematic formula. We found the acceleration. We converted the car weight into kilograms, and then we just use F equal MA to find the force. B, the time required for the change of speed. So I would use this kinematic formula. V equals V sub O minus GT. And we know it's coming to a, so that's going to be 0 because it's coming to a stop. And this is AT, still thinking about gravity. But our acceleration is 4.11 meters per second square. So this will go to, T is going to equal V sub O divided by A, which is going to be 11.11 meters per second, divided by 4.11 meters per second square, which is going to be 2.7 seconds. So that's part B. If the initial speed is double and the car experiences the same force during the braking, by what factor are the stopping distance and D, the stopping time, multiplied? Well, let's look at this formula right here. We're going to use this formula to find the stopping distance. And that will give us change in distance is going to equal, that goes on the other side, V sub O squared. That's the initial velocity. We know that it comes to a stop, so the final velocity is 0, divided by 2 times the acceleration. And this is going to go, we have to double the speed, so that's 22.22. 2 times the acceleration is going to be 8.22. And when you compute that, you'll get 60 meters. So divide 15 into 60. We're going to get 4. That's equal to 4. So by doubling the speed, I'm going to have 4 times the stopping distance. So that's answer C. Now what happens to the time? Well, we'll use this formula here again. T is just going to equal V sub O, which is 22.2 divided by 4.11, and that's going to equal 5.35 seconds, which is twice. If I divide 2.7 into 2.7 divided into 5.35, that's going to equal about 1.98, or a factor of about 2. That's your part D. So if you double the speed, you double the time to react. So that's what they want you to understand when they say there could be a lesson here about the danger of driving at high speeds.